like I just said, looks exactly the same, set of points, equidistant from a given point. That was a circle. But now I'm saying from a given point and a given line. That one takes a little thinking about and a little remembering some geometry. So, I'm giving you a point and I'm giving you a line. Where are the points that are equally distant from both? Just kind of logically, where would it have to, where's, okay, between the point and the line straight down, doesn't there have to be one in the middle that's equally distant? Is that the only one that's equally distant? Okay, so you're going straight over. So you're saying if I come out straight to the right of the point, I should have one that's equally distant to straight down? So yes, I would have, whatever I go straight over, I'd have to have the same distance coming straight down. I'm close, maybe not perfect. So the distance from here to here would be the same as here down. That's what you're looking for. The distance from the point to the line is always the same. You have to, when you measure distance to a line, you have to do it perpendicular. So that would be one. Would there be another? There would be diagonal, and there would also be one to the left. If I just did one to the right, there's got to be one to the left as well. Okay, diagonally which way? Going down? Yeah. So yes, if I came out here-ish somewhere, isn't that distance from the point to that, to our orange point here, down to the line, those should be an equal distance? Well, if there's one there, then I'd be one on the other side. Anybody think we're forming any shape here? Well, because if I connect those dots, what have I got so far? So it should be true. If I pick this point over here, that distance and that distance should be the same. In fact, if I extend the parabola, if I even let the parabola continue upward, I should even be able to come out here to a point on the edge, that point out there. The distance from the given point down to the line, those two lengths should be the same every single time. Every single point on the parabola is equally distant from that point and that line. Seems kind of amazing that it does that. Okay, but I'm going to get those lines out of there because they make us kind of messy. Okay, we already know the names of some pieces on here because you just did parabolas. So I'm going to ditch some of these. We already know the point at the base of the parabola is called the what? That's the vertex. Okay, the vertex is still a key point. We're going to worry about that vertex forever. Okay, the line down here, the line, now that we've used it to find it, we really don't ever care about the line much anymore. The line is called the directrix. I think of it as it directs the parabola. The parabola always curves away from the line. I'm not even going to bother to teach you how to find the equation of the line because really no one ever cares where that line's at. But we get so that we care a lot about where the point is. That point is called the focus of the parabola. That focus is a key concept for us. You're going to think, well, why? It's just this point out in space. It's not on the parabola. Who cares about the focus? Why bother about the focus? Well, I'm going to show you here in a moment. I got to switch over to the internet to show you some demos of this about the focus. But there's one other thing we need to get on here. Because we have the focus, we can also now measure how wide a parabola is. We measure the width of a parabola through the focus. That line gives us a place to say, this parabola is X units wide. That line has a name, and it's a lovely Latin name, so it's not particularly helpful. It's named the Lattice Rectum. I do not know the Latin meaning of those two words, but we usually just call it the lattice. But it's a measurement of how wide your parabola is at that particular point. So we're going to care about that. Okay, you're going to want that little white piece of paper I gave you with all those formulas on it. And for those listening by video, I know I forgot to give it to some of you. I'll post it as well. But I have it's this set of little formulas. You're going to actually just tape or staple this to your card once I get you a big size card, so that you just have all those formulas, since there's quite a bit to them. You'll notice on here down the side I have vertex, the direction of opening, we did that before, which way does it open, the line of symmetry, the coordinates of the focus, and then how to find the length of the lattice rectum. So the new parts will be how to do the focus and the lattice rectum. The question is, why do I have two columns? This first column, they've got the top of the equations, y equals. That's our standard vertex form we've been doing for the last 2 weeks. What's different in the right-hand column? It's x equals. So therefore, what to do to the parabola if I switch to x and y? Yes, now you can have a sideways parabola. Yes. So instead of going up or down, it goes right or left. If the number in front, if A is positive, it's going to open to the right. If A is negative, you're going to have it curving open to the left. So now we can have sideways parabolas. Get excited. But I need to go show you real world why we care, so that you'll appreciate why are we learning these lovely parabolas. I am going to kick over to the internet, though. And I hope this site's going to work. I forgot to show this to the last block, and it's Java, so I hope it's lovely. 6 connection problems, though. Seriously? Oh, I don't have time for all that. Okay, I may not get to show you that one right now. You may have to believe me, and I'll show you the cool demo when I get them to fix it. But it's at the moment not like, oh, shoot, I went to Internet Explorer. Never mind. Let me try one more time. It may work in Firefox. Cross your fingers. Nope, it hates my page. Okay, I'll show you that one on another shot. It's got awesome reflective properties. I'll let you guys take a guess. I'm going to give you a focus and a parabola. I'll show you my cool properties next time. It does a cool demo of this. Turns out parabolas have a certain reflective property. In fact, every single conic section reflects things depending on how it hits. On a parabola, turns out if you have a beam of light, a radio signal, a television signal, come into your parabola, straight into your parabola, when it hits the edge of the parabola, it bounces. Anybody want to guess where it bounces to? To the other side, like over here? Just Colin. Anybody? To the dot? What's the name of that dot? The focus, yes. It bounces to the focus. Doesn't matter where you are in the parabola. If I come in over here, once I hit the parabola, it bounces to the focus. Every single time. Okay, so think of something that might be out in your yard. It's got a fairly wide parabola shape. That's the bend of it, but yours would be three-dimensional. So yours would be in a circle with that kind of curve. A satellite dish. You may have a satellite dish if you get, or if you don't, if you live in town and you're getting cable TV, the cable TV people have a satellite dish somewhere, bringing the signal in. Yeah, they have the little pointy thing that comes out of the satellite dish. Guess where that point is located. It's at the focus. So what happens when that signal, the television signal comes into your satellite dish, it comes in, it hits the satellite dish, and it bounces it to the focus. That device at the end of that is the receiver. It is what receives the signal, and it then can transfer it into your TV. And so therefore, when the signal, wherever the signal comes into the satellite dish, it always bounces to the focus. So you don't have TV in Seneca, Kansas without a satellite dish, without a parabola and its focus. Same way when they send out signals, it shoots out signals and it shoots the signals out of there in all directions. They come out of here in all directions, they hit the parabola, and then they bounce straight out of the parabola every single time. Some of you have headlights in your cars. In the back of the headlight is a reflector piece that reflects the light outward down the road. When you are on high beams, when you want that light to go straight out ahead of you, the bulb is exactly at the focus of the parabolic reflector in your headlights. So that's why your beams cast straight out, because of this reflective property. Pretty cool, actually, what the reflective properties do. Well, actually, later on we'll be watching an awesome video about all the uses of parabolas or the conic sections in the real world. Not today. It's at the end of this chapter. After you have to know all the conics before we can watch it. Okay, I didn't mention this on circles. It's kind of common sense. Whoops, that's not going to work. What do you think the reflective property of a circle is? If I shoot something from the center of the circle toward the edge of the circle, where's it going to bounce to? Right back, exactly. Circles reflect everything right back to the center. So, yeah, if you want something to go out and come back, go out and come back, use a circle. But otherwise, it doesn't really reflect it anywhere. One other use of parabolas, if you use a microscope or a telescope, it receives the light. The telescope or the microscope gets light in, and then it bounces through there, and so that it's all the picture is focused right where your eyepiece is. There are mirrors inside it, and those mirrors may be curved as parabolas that are helping bounce the light through the telescope or the microscope, so that all the focus is right where your eye's going to see it. That's another use of them. So you will see many of them over time, and I will get my problem fixed with that website because I'm going to want to use it a lot. Okay, one other quick thing I want to show you, I hope, if this isn't going to crash and burn on me too. I used it last block. I'm trying to, Are you going to give me my 5 minutes or are you cutting me down? Yep. Okay. That's why I had Explorer open. I'm trying to fake it out because I don't want to pay for it. Yeah, baby. Here's a different browser and it works. Okay. It only gives me 5 minutes of free time per day to use these little demo things. So we have 5 minutes to work with this. You'll notice it's giving you a parabola here. At the moment, the focus is the green dot and the directrix is the green line. They're very close together. What shape is or I guess how wide is your parabola? Would you say it's narrow, it's wide? Somewhat normal. But if I start to take the focus and move it farther away, it makes my parabola get wider and wider. So the closer the focus, the closer together, or the more narrow your parabola is going to be. Okay, it will actually show me on here, when we were talking about it being equally distant from the point in the line, it's actually measuring them down here. It's telling you line 1 and line 2 are both 2.56 units long at the moment. If I go pick the point up here, and it's measuring line 1 to line 2, now they're both 8.54. Wherever I put that point, it's always equidistant from the focus and the directrix, wherever you go. So that kind of makes it visually a little easier to see. Turn that back. Okay. So, if you're watching here, we already know from what we did last chapter, if I start changing A, the number in the front of my parabola, you know that when A gets bigger, it gets narrow, make it smaller. Whoa. It got wider when I got to fractions. Then I went negative. So the more I change A, that changes my width of my parabola on there. What I want to do, though, is I want to make my parabola go sideways. How do we just decide what I need to do to get it go sideways? X and H need to switch. Now, I don't like this one, why they're leaving K over here, why they're not putting it over there on the other side. That's a little weird, but I can't control that. So now I've made it switch. My X's and H's are reversed. So now my focus is going over here to the side. My directrix is the green line going up and down. But still, if I start changing A, the number in front, I make it wider. The focus gets closer as I get more narrow. As I keep coming and get more narrow. If I go bigger, I can change it. So A changes it the same way. It doesn't matter whether you're going horizontal or vertical. The only difference that's changing is your X and Y coordinates to make it move. So there's not a lot of distinction on that one. Time remaining. But I want you to go away and stop my remaining time. Okay. So what I need you all to do, I'm only concerned about you're being able to find me the focus, the directrix, and then the usual stuff, the vertex that we've been doing. So we're going to, you need that set of formulas in front of you to do this, because I don't expect you to memorize all this. It's just too much. So if you would pull out your little white piece of paper there. Okay. I want to do one that's X equals. So what's that tell you that if this is X equals? It's going to go sideways. So since we've done lots of ones that go up and down, I want to do one that goes sideways. But this won't let me get rid of this, and it's in my way. Okay. So it's an X equals. So when you look at that sheet of formulas, your first thing you're going to go is, do I have a Y equals parabola or do I have an X equals parabola? We have an X equals, therefore you are going to follow this right-hand column. You're not going to look at these formulas over here on the left-hand column at all. Everything you need to do is right there. So we need to find the vertex, what direction. Notice the line of symmetry, since we switched direction, the line of symmetry is now Y equals, whereas before it was always X equals. Okay, and then I'll talk about the focus and the lattice rectum when we get to that part of it here. But once you know how to do this, this is not a major big event. You just have to be able to follow the formula. So here we go. The thing that's going to bug you the most, because you've been reading the vertex for so long with a Y equals problem, if I say to you on this one, what's the vertex? Wait, we know it has to have something to do with the 1 and the 2, but the question is how? I would vote for 1, 2. Okay. The 2, if it's in the quantity, you always put the sign. So the 2 becomes a positive. My question is that the X coordinate or the Y coordinate? What variable is in there? That's a Y, so that's telling me the Y coordinate. If there's a Y in the quantity, that's the Y coordinate. So Y is going to be 2. And if you take it out of any quantity, you change the sign. The 1, though, is out here. It's not in a quantity, so it doesn't change. It stays 1. So this vertex would be at 1, 2. That's probably the trickiest part of it. Okay. Is this one, we know it's sideways, is this one going to go right or left? It's the number in front. It's a positive 1/8. 1/8, so it's a positive number. Okay, so if you're going sideways, the positive side of a coordinate system is to the right. The negative side is to the left. So if that's positive, it's going to go right. Okay. So now, watching that column on that set of formulas, if you do the line of symmetry, is it X equals or Y equals? It's Y equals. And since it's Y equals, it goes through the Y coordinate of your vertex. So it's 2. All right, now the new stuff. How do you find the coordinates of the focus? Let me draw a rough sketch of this somewhere. I want that circle out of my way. It won't let me erase it. I think I can delete it. There we go. Okay. So if we have this parabola, and we know, this is just a really rough sketch, the vertex is 1 over 2 up. We just figured that. That's the vertex. We know it's curving off to the right somewhere. The focus, is the focus going to be to the right or the left of the vertex? The focus has got to be out here in the middle of the parabola. So we know the focus is over here. So all I need to do is I need to take the vertex coordinates, and don't I just need to move over just a little bit to the right to get to the focus? So that's why your formula says do h plus 1 over 4a, comma k. H and k are the vertex. So you know we have the vertex is at 1, 2. It's saying add a little bit to the x-coordinate so you move over. And it turns out that little bit you move over is 1 over 4 times a. What was a in this problem? That number in front, the 1/8, that was what we were finding. Now, the biggest problem I have with this is don't mess up your arithmetic with fractions. First, take 4 times 1/8. You realize that's on the bottom of this overall fraction. 4 times 1/8, doesn't the 4 cancel in there? And I would be left with 1/2. So I have 1 divided by 1/2. How do you do 1 divided by 1/2? You got to, don't you, when you divide by a fraction, you have to flip it over and multiply? So it's really just 1 times 2 over 1. You just flipped it over. So it's just 2. And then 1 plus 2 is really 3. And so it actually turns out the focus is at the point 3, 2. So in reality, it moved over 2 units to get to the focus. That's all that happened. But watch the simple arithmetic on that. That's where I see people mess up. Okay. Last but not least then, the lattice is easy. What does your formula sheet say to figure out the lattice? How wide this thing is? It says do 1 over a. Okay, guys, easier way to do that. Who was it? Oh, okay. 1 over a? Okay. Well, I'm almost done. 1 over a. Please take your a number, your 1/8. 1 over is just the reciprocal. I mean, you could do the reciprocal of that. Flip it over. What's the reciprocal of 1/8? 8. So, I mean, you can write it out longhand, 1 divided by 1/8, but it's really just 8. Just flip it over. That's all you got to do to get the lattice. No big deal. Now, does that make sense? We know that for the fraction that was 1/8, so that should have made our parabola wide. And it turns out then it's going to be 8 units wide. So, because you're flipping that fraction over, it makes it get wide at that point. So it kind of does have a connection. Okay, last little thing, and I need to give you a tiny bit of graph paper. You don't have much to graph today, but I do need to give you a little. To graph it, you could do it the old-fashioned way with the 149 that we just did. You can do it that way. But actually, you've got all the information you need right here that you can draw the graph with doing this, and you don't even have to do the other stuff. All you need to graph it, you got the vertex, the focus, and the lattice, and you can draw a graph of the parabola with those 3 things. I'm going to write you a set of steps. These steps should end up on your card. So if you want to graph a parabola, all you have to do is plot the vertex, plot the focus, and then put half of the lattice on each side of the focus. And I need a tiny bit of space to do that in. It doesn't take much. I'm going to kill this up here. Okay. So, literally, and granted I should get some graph paper out, but our vertex is where? 1, 2? If you want to graph this now that you've done all that work, okay, 1 over 2 up. That's the vertex. Where's the focus? 3 over 2 up. That's focus. Okay? The lattice was 8. So it'd have to be 4 on either side of the focus. That would tell you how wide it is. So you would just have to go up 1, 2, 3, 4, and down 1, 2, 1, 2, 3, 4. Just go 4 on either side, and then you can just, I mean, it's not a super accurate parabola, but you can get the parabola through there by just doing that much. You don't have to go back and do all the other work. So it's a quick way to get a parabola. I'm not going to get that excited about that because we've done plenty of parabola stuff already. So you will enjoy it immensely. These are great.